with you as well. Okay, most likely your mind isn't on math now. Okay, but nevertheless, let's go through. So yesterday we gone through this fundamental theorem of calculus, which is kind of a big deal because it demonstrates that integration and differentiation, they are reverse operations, right? So when you integrate a function small f, you get the antiderivative big F, and then if you were to differentiate big F, you get back the original function small f. Okay, so this is the important statement of FTC. Okay, basically they are inverse operation or they are reverse operations pertaining to differentiation and integration. Okay, so much so that if you look at this expression here, now actually when you differentiate and then you integrate, that means you differentiate and integral, right? Then you're just going to get back the original integrand. Okay, the integrand is the function that is inside the integral. Okay, you're just retrieving the original function you want to integrate in the first place. Okay, so this part, the derivative of an integral is just returning you the integrand. Okay, so therefore you get back the function f. Okay, so basically this says that when you differentiate an integral or when you integrate a derivative, you are not doing anything effectively. You are just getting back the original function that you are operating on in the first place. Okay, so this is the big deal about FTC. And we applied them to some of the examples yesterday. So today we are going to state again what is the essence of integration. Now the essence of integration, this is very important, okay, because if you understand this, then you will be able to effectively know when you need to integrate, okay, because the counterpart of integration is actually multiplication, okay. So later on I'll make that statement clearer, but the essence of integration is really to sum up all the small changes in the function that you want to describe the total change with. Okay, so let's say this big F, you are trying to describe some total change, right? Because big F can be a change function, right? A function of changes, for example. Okay, so therefore, if you sum up all the small changes in big F, then you are really trying to get the total change. Simple as that. Okay, so in this case, you can see that, right? This small f times dx is actually your df. This df, okay, hold on. I need to restart this again. So as I was saying, this df is actually your f dx. This df is your f dx. Okay? Why is that so? Because the big F dx is exactly small f. So from here you can see that, right? df equals to f of x dx, right? Okay? So that means the big F dx equals to small f of x. Okay? Because we mentioned that big F, for example, if big F is the antiderivative or the integral of small f, then small f must be the derivative of big F. Okay? So therefore, this is evident from the statement of the derivative. Okay? So this df is actually the small changes, right, in the integral function. Okay? So you sum them up, you get a total change. Yeah, so this part is important as we have gone through yesterday. Okay, why is it I say that just now? The counterpart of integration is the multiplication. It is because if, let's say, you got a function that doesn't change throughout the change in the independent variable. Okay, so let's say when you're trying to get work done, right, and your force is a constant, then obviously the force doesn't change along x, right? X is your independent variable. So therefore, if that is the case, then you can factorize out the f. So therefore, effectively, you get force times distance moved. However, if you have a force that is changing along x, then you cannot factorize the f of x out because you are integrating with respect to x, what? Okay, you cannot factorize that out. So therefore, you have to perform an integration, okay? So keep in mind that whenever you have something that is changing along the independent variable, and you are trying to find the total change, right? You have to perform an integration instead of just doing a multiplication, okay? So later on in the tutorial, we'll have more examples demonstrating this concept. So this is where we stopped at yesterday, okay? All the integrals of the elementary function. Basically, this is like a lazy way to get our integration table. Okay, if you have a differentiation table, right, you probably know that you can use it as an integration table by just reading it the opposite way. So if you have left to right, right, it's a differentiation table, then right to left will be just an integration table. Okay, so you can see from here, because we know that, for example, this guy, when you differentiate x to the power of n, right, you bring down n and then the power minus 1. So you see the first step is that you bring down m. Bring down n is the first step. Then power minus 1 is the second step. So which means when you integrate x to the power of n, you must do the reverse, you know. So let me label the step. So step 1 is you bring down n. Step 2 is the power minus 1. Okay? So what happens in the integration? Because the integration is the reverse what? So which means you must start from step 2 first, because you're going backwards, right? So which means the power you must go and plus 1. So you can see in the integration process, your power must plus 1 first, okay? Because you are reversing. You are reversing 1 to 2. So you must be 2 to 1. Can okay? So therefore you must have the first step, right, which is reversing 2. Then the second step, because you multiply, right? I mean, the first step is that you multiply here. So therefore, the second step here must be that you divide. So this is the second step. Okay? So let me draw the sequence here. Okay, maybe I should change this. This will make it clearer. So you see, it is always like step 1 to step 2. So step 1 to step 2 is the differentiation, d dx. So when you do integration, it must be step 2, go back to step 1. Because that's the reverse one. Okay? So this one is an integral. Okay? I just keep the number allocation because I think probably it's clearer that way. 1 to 2 in differentiation, 2 to 1 in integration. And the same applies vice versa. Okay? So you can see the rest of the integrations are just trying to reverse the differentiation process. Okay, because we make use of FTC. So this is what we have gone through for the examples on the evaluation of the integrals. And this is really quite straightforward, because I believe all of you have done some integration last time before, right? So this one I won't go through in too much detail. It's quite straightforward. Okay, so this one you multiply out, then you get 4x cubed plus 4x. Then after you integrate 4x cubed. So 4 is a constant, you can just keep it. You can see x cubed, right? You go and plus 1, become x to the power of 4, divide by 4. Okay, so you plus first, then you divide. Okay, don't go and divide first, then you plus, right? That means you're not following the correct order of things. Okay, then the same thing goes for the 4x. Integrate, you get 4x squared over 2. And because this is indefinite, so therefore you have to put a plus c. Okay, and then just simplify the answer. Same thing goes for b. So split up the fraction. Okay, you get 2 over x squared minus x over x squared, you get 1 over x. Then you integrate accordingly. So integration of 1 over x is your ln x, because differentiate ln x is 1 over x. Okay? So then the rest are pretty straightforward. Then the third one, 3 to the power of x. Now this 3 to the power of x, you have to be careful. Okay, because when we differentiate 3 to the power of x, right, we must times ln 3. So when you differentiate a to the x, you must times ln a, ln of the base. That means when you integrate, you must divide the ln a away. So therefore this is dividing by ln a. Okay, so once again we are doing the reverse. Right, so therefore you have 3 to the x divided by ln 3. Okay, then the rest is pretty standard stuff. Any questions on the examples here? Just use your integration table directly, more or less directly. Looking good? Okay, now let's take a look at an application of integrals, which is on your kinematics again. Okay, so during the differentiation topic 3, right, we also looked at kinematics. Because from there, we know that The rate of change of displacement is your velocity. The rate of change of velocity is your acceleration. So, which means if you multiply by the dt term across, that means or throughout, then you are getting ds equals to v of t dt. And this makes total sense. Because if you take the velocity, now what's happening here is that you have to read it like that. ds, how come you can take velocity times time? How come a displacement can be given by velocity times time? Only when velocity is constant what? This is what I mentioned just now. Okay? So indeed, this is the case. You see how beautiful this is? That means even though your v of t is changing, so let me just draw a diagram to illustrate. So let's say this is your velocity, v of t. Now, that means at every t, you are treating the v of t as a constant. This height is v of t. I know it is not a constant. Obviously, it's not a constant because it's changing. What? Okay, but at every t, you have an instantaneous change in time dt. So you can observe that if you take this v of t times that instantaneous change in dt, okay, obviously, I'm not describing it in the most correct sense. Since dt is like a small infinitesimal change, it's not exactly instantaneous. Because if it's instantaneous, then there's no change. What? Agree? So therefore, what I'm trying to say here is that, right, this dt is so small, you know, because dt approach what? Dt approach 0. So if dt approach 0, that means this dt is like no change, you know, but there is a change. There is a change. Okay, it's not exactly 0 because now we know what's the difference between exactly 0 and a limit. The limit is 0, but it's not 0. Okay, that's why we term it as dt. So therefore, this area is your ds what? This is your ds. So you see how beautiful this is. Even though your velocity is changing, but by imagining the change in time as an infinitesimal change, you can treat this v of t as a constant over the small change dt. So this is a very beautiful idea about this derivatives. Okay, so this is treated as a constant velocity, constant v of t. Okay, over a short span of time dt. Okay? Is that right? So of course, if this is some finite change, then it will be delta t. Okay, but we know if this is delta t, then your change in displacement is more of an approximation. Okay, but if your delta t is getting very, very small, then you can treat effectively that the v of t is a constant. It approaches a constant. Can I? Okay, good. So, hopefully you agree with what I just mentioned. So the same logic apply to dv equals to a dt, yeah? Same thing. Okay, so if you have acceleration that can be treated as a constant over some small change in time dt, then this is really just giving your change in velocity. Okay, so therefore, we know that this ds is a small change in displacement, right? Infinitesimally small change in displacement. So if you sum up all the small changes, then you get the total change. So this is the total change in displacement. Is that all right? S of t is your displacement function, ma? Can So the same logic applies to v of t then. Okay? So now we are going to look at how this very simple idea, this is so simple, okay? Just getting from the derivative and then multiplying throughout and then integrating both sides. Okay, you get your displacement and your velocity functions respectively. And we can actually use this very general understanding to derive your kinematic relations. Okay, so which means if you have the velocity function, you can integrate to get displacement. If you have the acceleration functions, you can integrate to get velocity, right? So let's consider what you have gone through for your physics classes. Let's say you have constant acceleration a. So if you have constant acceleration, what would be the velocity function? You probably have learned that v equals to u plus at. Okay, so how did that come about? Exactly from integration. Because the velocity is just integrate acceleration dt. We just established that in the earlier slide. So what's a? A is a constant because it's a constant. So if a is a constant, you can factorize it out, right? So you integrate 1 dt, you're just going to get t plus c. So therefore, you are going to get the acceleration a times t plus the acceleration a times c. C is just a constant of integration, that is. So since c is just some arbitrary constant, right? So I can treat this arbitrary constant c times a as another constant d. I just treat that as d lah. So now my velocity function has an unknown d, unknown constant d. So how do I find that constant d? Is simply by considering a known point, a known condition. Okay, in this case, if your t is given at 0, that known point, you are getting the initial condition. So this green guy, right, is the initial condition. So you can see here that if you substitute t equals to 0, you are going to get the velocity giving you v naught. That is what we call the initial condition. Okay? So now, notice that when you sub in 0, you get a times 0 plus d. And this a times 0 plus d must be equivalent to v naught. So you have found that d exactly equals to v naught. So indeed, your complete function for velocity is at plus v naught, which is your u plus at lah, because you are using u as your initial velocity. Is that right? Can So that's the first relationship that you have been using for your physics. Next, what is the average velocity then? Okay, this one important. Okay, very important. Now you see, the average velocity, from what we know about averages, it must be total divided by total. So average velocity clearly would be the total displacement divided by the total time taken. So what is the total displacement? The total displacement must be the area that is underneath the velocity function. What? So your velocity function is v naught plus at, which is really just a straight line, because your independent variable is t. So therefore, it is really a straight line. So now, right, how do I get the total displacement? Well, I can integrate what? Right? Which is what we just established a few slides back. Okay? Total displacement is a sum of infinitesimal displacement. So just integrate to get the total displacement. How? You already obtained your velocity function. So why not you just integrate your velocity function to get the total displacement function? So you can see from here. Now this total s is this integral. Then the total change in time, right, is t minus 0, right, because we are looking at from t equals to 0 to t equals to t. Okay, so I have 1 over t minus 0, this total change in time. So, what is this? Now, this is my velocity function, okay, and I just replace the independent variable from t to tau, okay, and this is trying to not confuse with the limit t. This one I mentioned before, right, which is from here, change t in v of t to tau. You can change to anything lah, can be x also, doesn't matter. Okay, but the convention here is typically the counterpart, the brother or the sister of t is tau. They usually use tau lah, I tell you. Okay, so change the t in v of t to tau to avoid confusion with the limit t. Is that right? Okay. To be very honest, you don't change, I also won't mark you wrong. Because some people, they don't like to change, so they don't change. But you have to be careful later on when you sub in, right? T equals to t, so actually that's actually fine as well. Can Okay? So you see what happens here? So this is like v naught plus at become v naught plus a tau. So now I'm integrating respect to tau. Can So therefore I'm looking for the total area. So then I integrate, sub in limits, then I'm going to get this expression. Okay? So this expression, if you realize, I can factorize out t. So if I factorize out t, I'll divide by t, and that cancels exactly off. And you notice that I am getting at plus 2v naught. But at plus 2v naught is just at plus v naught plus v naught. Then this at plus v naught is just v of t. What? So that gives the average velocity. So currently you may be wondering, how come you go through the integration process? Because there is a simpler way to get it. Because if you look at the graph, isn't it ridiculously obvious that the average velocity, because this is a straight line, it must be in between exactly v0 and v of t? Because this is a straight line, what? So therefore, it must be v0 plus v of t divided by 2. I mean, just looking at the graph, you know already. Obviously, that's clear. But that's only if your v of t is a straight line. If your v of t is not a straight line, then you cannot do just dividing by 2. So the average value, always you have to generally integrate, okay, and dividing by the total change in the independent variable. So this is the average value thing. Okay, so to find the average value of a function over an interval a to b, right, you have to perform an integration and then just dividing by the interval. So this is effectively converting this area, this blue area, into a rectangular area. You notice or not? Because this area is this blue area. So if you divide by the width, that means effectively you are getting an average height. Okay? So the average height is the y average. So this is the logic of the average value right here. Is that okay? Can. So this gives the average value. Any questions? Okay, looking good. So then you also have another two famous formulas, what? Because if you have v equals to u plus at, then you also have s equals to s0 plus ut plus half at square. Still recall? I think you learn it as s equals to ut plus half at square. Because your s0 is 0. So how do you get that? Easy peasy. You just integrate the velocity function, right? So nothing much. Throw into the velocity function, into the integrand, integrate, and then you use your initial condition. So you found c, which is the constant of integration here, and then you just sub back c equals to s0. Okay? So that gives your displacement function then. Then if you were to combine v of t and s of t, right, you get rid of the t, then you are getting the v square equals to u square plus 2as. So this is not difficult. Basically, what we do is that we just isolate the t from the velocity function. You see, then I just sub in the t into equation 1, which is for your displacement function. And then you just simplify, multiply out, simplify, you can get the answer here. Okay? So I've demonstrated how you can derive the 4 basic kinematic equations for constant acceleration. So very important. If I don't give you constant acceleration, you better don't use any of the 4 relations. It's only for constant acceleration. If the acceleration is not constant, none of the 4 applies. None of the 4 formulas apply. Okay? But this will always apply. This will always apply, regardless of whether your acceleration or velocity is constant or not. Okay? So this is the most general. The integral is the most general. Okay? Any questions? Okay? Moving on. Actually, that's it. Okay, so we are done for this topic 4. Meaning to say, as I have mentioned, you'll be tested in your midterms until the end of topic 4. Okay? Okay, this average value, I better put a star here. There's a reason why I put star. Can I just make it clearer in case it's not clear enough. Star plus box, that should be, if you still don't know, I don't know what to say. Star plus box, you know. Okay? Right, so let's jump over to the tutorial. Okay, I know that because of your test later, most of you didn't have time to try the tutorial questions yet. Okay, so certainly I'm not going to go through many of the questions. Okay, so probably I'll end within 1 hour so that you have more time to prepare for your test later on. Is that okay for you? Or you want me to go through more questions? I mean, we still have a lesson next Thursday. The lesson next Thursday, right? We will be going through the rest of tutorial 4 as well. I mean, we can go through. So I think that's a better option, right? Okay? You focus on what is the challenge in front of you first, which is at 6 o'clock. Okay? Yeah, so question 1 is, okay, question 1 I didn't go through, but maybe I just go through with your class a little bit so that to give you a bit of a head start, okay, on how to evaluate this integral. So you're supposed to sketch the area represented by the integral below and identify the shape. Then after that, you set up the Riemann sum. Then the Riemann sum, I think I leave you to set up. Okay? Because it's actually, if you look at the terms, right, it's very similar to the lecture examples. Okay, but what's important is that I want to show you what is this shape lah. Okay, so you see this function, the integrand function, is what you are trying to find the area underneath. So this is f of x. Let's call that f of x. Okay, your integrand function. So now your graph looks something like that, right? I mean, if you don't know how the graph looks like, it's perfectly fine, but you just plot in a few values, then you roughly will know what. So what is this? This is gradient times x plus a ma. Okay, b minus a is just constants, Then over h is another constant. So a constant x plus a. So this has to be a straight line, what? So therefore, your a must be the y-intercept. You see? Your a must be the y-intercept, because it's plus a, what? Then what is the gradient? The gradient is b minus a over h. So which means, if this is a, then this must be a lah. I mean, the distance from the origin looks roughly the same. Can this must be a lah. Right now. Then b, okay, let's take it as b is more than a. Oh, by right, I should have stated that. Okay, let's say b is more than a. So which means you are having this b here. Wait a minute. Oh, my fault. I interpreted it the wrong way. This should be changed in y. So therefore, let's call b here. Okay, so b is more than a. So then you can see that this is b minus a. So therefore, this is change in y over change in x. What? Okay? So therefore, what is the change in x? Now, you can see that, right? If your x, okay, so let's make it such that, right? Now, you want to know what is the, what do you call that? What is the points along your x-axis. So how do we get that? So you can see that when your x is 0, then you have the y-intercept a. When your x is 0, this whole term is 0, what? Then you have just a ma. So which means at x equals to 0, you have the height a. Then when your x is h, so this becomes h divided by h, which means that there's a 1. Then b minus a plus a will give you b. So which means at x equals to h, you're having the coordinate b, okay? Because at x equals to h, so let me just write. So you have b minus a over h times x equals to h, then plus a. So this is b minus a plus a. So obviously it's just b. So therefore you can see I draw the point at b. So that means you have two heights already. One is at a and one is at b. And this f of x must be what? mx plus a what? So the m is the gradient. So now you can see that I draw this. So this is my gradient m. So this whole thing is the gradient m. So this is the gradient m. And therefore f of x must be this line here, this straight line. So this is my f of x. Any objections? Yeah, so if you have no objections, then really this integral is just trying to find the area underneath this trapezium. Okay, so we notice that this is a trapezoidal area. So we are looking for the area underneath the trapezium. Okay, equals to the area. Is that right? Any questions? So you have no questions, then the rest is a bit mechanical already. Right? So I'll leave you to try the rest. Okay, trying to derive the area Riemann sum here. Okay, this is the area Riemann sum. And then if you simplify, or you can just inspect using an area formula, it's really just a plus b times h over 2, which gives your trapezoidal formula, trapezoidal area formula. Okay, that's how the formula comes about. It's from integration. Okay, so that's for question 1. Okay, question 2 I didn't do, because it is the same kind of question as the lecture example. Okay, so this one I won't go through, you try first. Okay, question 3, I went through D. D is a bit difficult. So let's look at the approach. Now, first of all, you have to first of all recognize that this integrand function is actually belonging to a part of a circle. Okay, let's go through step by step. Okay, now let's consider that you have a circle of radius 6. Okay, so if you have y squared plus x squared equals to 6 squared, right? Because this guy is y squared plus x squared equals to r squared, correct now? So that means your circle is centered at the origin with radius 6. You see that? So then from the topic 1, last part on transformation, do you recall that when you make the x become x minus something, you are shifting the area towards the left or right? So when you have x minus something, right, you're actually shifting the entire graph towards the right. Okay, so this is from your topic 1. X minus a means you shift right by a. So you can observe here, right, is that I have this x changed to x minus 6, right? That means I must shift this whole circle to the right by 6, because it's minus 6 here. So that means my center of the circle now becomes at 6, 0, coordinate 6, 0. The radius no change, because the radius is still 6 square. Is that okay? Can So therefore, if you look at this circle, right, and you try to isolate the y term from here, so what we do is that we move the x minus 6 term across, and then we take root both sides, and you're going to get the y equals to plus minus root of this function. Okay, why plus minus? Because you got a positive half and a negative half pertaining to value of y. But if you look at this integrand, there's only a plus, there's no minus. So it makes sense to interpret this as only the upper half of the circle. So because it's the upper half of the circle, right, and you're integrating from 6 to 12, so that means you are looking for the quarter area. So then obviously we know that the area of a circle is pi r squared. So you just take it, divide by 4, and therefore you get 36 pi over 4, you get 9 pi. Is that all right? So this integral is going to give you 9 pi. I mean, if you integrate this in decimals, or you can integrate this by yourself, right? And you sub in the limits, you are exactly going to get 9 pi. Okay? Obviously, because you are looking for the same area underneath the circular curve. Is that all right? Any questions? Okay, good. So for question 4. Question 4 is about expressing each limit as a right Riemann integral. Okay, and I went through D. Why is that so? Because D is not so obvious. What is the delta x? Okay, because delta x, what I'm trying to say here is that whenever you try to convert, the Riemann integral, right, you need to identify the change in x first. So then the change in x will be something over n, because change in x is always b minus a over n. It means you take the limits, right, in the x direction, then just divide by the number of partitions n, correct not? So that means you are looking for this something over n. So you can see this question, right, 1 over n, is that something over n, or? Then this 3 over n, is that something over n, or? So it's very clear, okay? But if you look at question D, I don't know where is the something over n. Because this guy is over n squared plus I squared. Then there's no over n term here. The rest all got. You can see this one is over n to the power of 6. So you can take out like 1 over n. Okay, then this n become to the power of 5 times n. So there was no problem. Then this one 5 over n, very clear. This is your delta x. Then this is 4 over n, very clear also. But this guy got no over n. So the truth is, if you don't see an over n, right, then just create it yourself. So how to create? Factorize all. Okay, so see from here. So what I do is, I know there's an over, I know there's a 3n here. So I can easily factorize out an n square. If I factorize out n square, then I know n square divided by this n here, I'm going to have something over n here. So which is what happened here. So if I factorize out n square, right, then this bracket must be 1 plus I square over n square. Because if you multiply in, then you get the n square plus I square. But once you get the n square here, then you divide by the n at the numerator. So you have 3 over n already. Of course, you can state it as 1 over n. Or you can state it as 3 over n. Doesn't matter. Okay? So from this part, right, I have used delta x equals to 1 over n. That means I don't include this 3. Okay? Maybe you can include the 3, but I think later on you have to do a bit of changes here. Okay? Which is totally fair as well. So you observe that now my delta x is 1 over n. then my xi is always a plus I delta x. Never change one. So I already have my delta x. So I sub in. So therefore I get a plus I over n ma. Then when I get a plus I over n, I must choose what is a what. I always need to choose a. So I'm going to choose a equals to 0. And then xi must be I over n already. So once I see this I over n, and I see this I square over n square, I know this term, orange box term, must be xi square. So my function must be what? Now, my function must be 3 over 1 plus xi square. There, this is my function. No? So therefore, once I identify the f of xi, then I know what is my a and b, a to b, integrate. Then I put in f of x, then that's it. That's the integral. So the limit of the sum, right, the Riemann sum here is this integral. Okay, so in a nutshell, if you don't have an over n, just squeeze it out, or just factorize it out, or just, include it, and then make some changes to the rest of the terms. Any questions? Okay, so this is for question 4. Okay, question 5. Question 5, I did the second one, because this one not so easy. So let's look at the approach here. So basically, we are trying to prove, we're trying to show that, right, the integration over a symmetric interval from minus a to a, let me label the thing. So this is from minus a, integrate all the way to a. Now this minus a to a, if you integrate, right, is going to give you 0 if your function is odd. Okay, and this is very clear from the graph, right? Because the positive area will always cancel off exactly with the negative area if your function f is odd. Okay, so I think this one is easy to see from the graph. But it should also be able to be proven mathematically. Okay, so what's the proof? The proof is making use of the definition of an odd function. So you see, now this integral, right, I split up the integral into 2 parts. One, right, is the first part from minus a to 0, this part. Then the other one is from 0 to a, which is the second part. So basically the red area and the blue area sum. Okay, now, if I look at this expression, obviously I cannot just say that, oh, this equals to this and then minus of exactly equals to 0. Because you look at this thing, this is minus a to 0, right? This is 0 to a. It's not the same thing. What? You cannot say that both areas are the same. Okay, this is what you're trying to prove. You can't just make use of the result directly. So now, we make use of the understanding of an odd function. Now, what's an odd function? Odd function means f odd of x equals to minus f odd of minus x. Now, this one we discussed in topic 1 before already. So we just sub in the f odd of x as minus f odd of minus x. So you can see that I didn't change anything. I just sub in the definition of an odd function. Okay? Then I swap the limits. So if I swap limits, right, I can take out a negative. Okay? I just swap the upper and lower limits. So the negative times this negative will be positive 1. Okay? So now I'm having integration from 0 to minus a, right, on the f odd of minus x with respect to x. So this is a problem to evaluate. Why is that so? Because you are integrating with respect to x, but yet your f odd, right, is with respect to minus x. So what we need to do is to make this change of variables, or what we call substitution. We just let y be this minus x. Okay? Now if y equals to minus x, that means dy dx must be minus 1. Just differentiate. Okay? So this must be minus 1. That means this dx must be what? This dx must be minus dy, because I just multiply the dx across. Then I bring the minus to the other side. So I get dx equals to minus dy. So you see the magic happen. Okay? So just look at, okay, forget about the limits first. Now you look at this. So this becomes f odd of y, because minus x is y. Then dx is minus dy. So I just sub minus dy. Then from here, right, I must update the limits also. Okay, because now I'm integrating respect to y already. Because integrating with respect to y, function of y with respect to y. So now the limits must be updated for y. Because this one, right, the limits is for x. So which means at x equals to minus a. So what is your y limit? your y limit must be minus of minus a ma, because it's minus x what, your y. Okay? So your y becomes a now. Then at x equals to 0, y equals to minus 0 is still 0. So you notice that the limits are now updated to 0 to a. So this is the magic. Minus can be factorized out. You get this. Now, if you look at this and this, they are exactly the same. You see? This and this. This and this, right? They are the same what? Because, remember, I mentioned that when you integrate function of y dy, or you integrate the same function of x dx, or you integrate the same function of t dt, it's the same. Because the function gives you a curve. I don't care you d what, right? You're just looking for the area under the curve from 0 to a. That's all. Okay? So indeed, this is a negative area because of the minus sign here. Then this is a positive area. So minus plus positive, you get 0. Exactly 0. Okay? So the technique demonstrated here is called integration by substitution. Okay? Not to worry about this, if you find this a bit fuzzy, because topic 5, we're going to delve more into this integration by substitution. Okay, why is it that we need integration by substitution? It's because every differentiation rule has an inverse in the integration counterpart. Okay? So therefore, integration by substitution is actually the reverse of the chain rule. You learn chain rule, right? Correct or not? In the differentiation process. So therefore, there is a reverse chain rule. Reverse chain rule is exactly integration by substitution. Okay? This is the substitution. Okay? We let y be something. So that's the substitution. Can So not to worry, this one we'll delve more into it in topic 5. So just give you a sneak preview here. Okay, then for question 6, I only went through 6 each. Okay, because 6 each is a little bit more difficult. Okay, the rest are pretty standard, following the examples that we have gone through in the lecture. So let's look at 6 each. Now, 6 each is that, first of all, you got to recognize that, okay, so by the way, you're trying to get h prime. H prime means, right, you got to differentiate this integral. So obviously using FTC lah. But you must notice that this is x times f of t. X times f of t, that means this x got nothing to do with this t, you know. Okay, I repeat it again. Because you are integrating, you are summing with respect to t, so the x, you can treat it like a constant. Okay? So a constant with respect to t, right, means you can factorize it out of the integral. So x is like 2, for example, a constant. So the constant can factorize out of the integral. So you can see what happened here was, when I differentiate h of x, I am differentiating a function of x times another function of x. Is that right? So it's x times a function of x. So therefore, I need to use the product. So this is product rule in conjunction with FTC. That's why a bit challenging. Okay, but if you get familiarized with this is also fine. You see, so now if I differentiate x, I hold the integral. So I just get this integral. Forgot my 3 here. Okay? Then subsequently, now I hold x, then I must differentiate the integral. So if I differentiate the integral, right, all I need to do is to use FTC. So you can see that I use FTC here. Okay? Because differentiation of the integral. But then, because my limit is g of x, what? So when I sub in, I'm getting the area function, sub in g of x, then minus sub in 3. So from here, if I d dx, this a of g of x, I must use chain rule. So hence, the end result is this expression. Because a prime is just f. Okay? Because you integrate f, you get a prime what? So that means if you differentiate, if you integrate f, you get a. So if you differentiate a, you get f. So this a prime will be equivalent to f. Any questions? Can So therefore, the takeaway for this particular question is you can be tested on fundamental theorem of calculus together with other rules of differentiation. For example, we use product rule here and we use chain rule here. Okay, just use whatever rule you have or you need accordingly. So that's for question 6. Okay, the rest you try. Question 7, important. Okay, question 7, I think is the last question. Very important. Why? Because once again, it is demonstrating the physical meaning of an integral. So I have told the earlier class that I'll be testing you on this. Okay, meaning to say, I don't tell you it's an integration. I ask you to find something. Okay, you are supposed to know that you have to integrate to find that something. Alright, so make sure you understand what is the meaning of an integral. So let's look at 7a. So of course, as you go through more examples, I think you'll get the idea. So if let's say I prime represents the new daily COVID-19 cases, now state the meaning of this integral of I prime with respect to t. Okay? So if you look at what is I prime is di dt. What? So if you take di dt times this dt, because this integral means sum only, sum of this thing, what? Correct? So therefore, this is di, what? Because like dt and dt can divide away, so it's just di. But what is di? Di is actually the small increase in total cases per day. Why is that so? Because I prime is the new daily cases. I repeat that again. I prime represents the new daily cases. So if you take the new daily cases, I prime, multiply by, for example, dt is, let's say, on the daily basis, then after 1 day, you have a small increase, a daily increase in the total cases. Is that all right? So that is small increase in total cases. Correct. Small increase in total cases per day as the day progresses. Okay? So now when you integrate, what does that mean? It means you integrate from day 0 to day 30, let's say over a month. All right? So you are summing up all the small increase in total cases. So that means this must be the total increase in the COVID-19 cases from day 0 to day 30. Is that right? So you see the trick is always to look at what is the integrand function here, multiply by the d something. Okay? Then after that, you just treat it as a sum, and you'll be able to extrapolate the meaning easily. So part B. So part B, okay, now you see, Q of T, right, represents the volumetric flow rate of water flowing into empty tank in cubic meters per second. So Q of T, the unit is in meter cube per second. Now, what is this? First of all, first step, check out what is your Q of T times dt. Now, because this is meter cube per second, so you go and times dt is what? dt must be in seconds, because it's small change in time, what? Correct or not? So let's say it's in seconds. So that means this is meter cube per second times second. So it's meter cube, So what is meter cube? That means it's dV. Small increase in volume of water in the tank after time duration dt. Okay, so after dt, right, some flow rate, some flow of the water flown into the tank already. Then you have a small increase in the volume of water. So if you understand that, then you just integrate this dV. That means you are looking for what? The total increase in the water volume from t equals to 0 to t equals to t, You see? But then, this integral is multiplied to density, because density of the water in kilograms per meter cube. That's your rho. So obviously you know that density times volume must give you mass, what? So this integral times density must give you the total increase in mass of water in the tank from t equals to 0 to t equals to t. Any questions? Okay, hopefully you get an idea. Okay, last one. Okay, this one difficult. So I go through step by step. Okay, now you see. Oh, sorry, this is not the last question. Still got one more. But this one, fast one. Okay, now you see this rod has length L and cross-sectional area A. So I just draw this rod here. Now, if the material density function is rho x, where x is the position along the rod from one end, state an expression for determining the mass of the rod. Okay, now, the issue here is, right, the density is not a constant. Density need not be a constant throughout a material. The material can be having changes in density. It's just like the column of air above us. At higher altitude, higher height, right, the column of air is of a lower density. At the sea level, the column of air is at a higher density. So density can change. No issues with that. Okay? So now if you look at this thing, so we have cross-sectional area A, and then at length x, right, at position x, right, let's consider a disk. So this disk is so thin, right, because it has width or thickness dx. So much so that you can treat the density as a constant over this small length dx. Okay, it's the same idea as what I've illustrated just now. So because of that, right, we ask the logical question, what is the mass of this disk? Because if I know the mass of this disk, I can just integrate or sum up all the masses of all the disks along the rod. Then I get the total mass already. I just sum up all the disks lah. Okay, so you can see this is a very beautiful idea. So the mass of one disk must be density times volume. But what's the volume? A dx what? Must be the cross-sectional area A times the thickness dx. So you can see the volume of the disk must be A dx. Then you take the volume times density, obviously you get the mass. Can? So therefore, if you have written down the mass of the disk, which I call dm, okay, so it's like what? Why I call it dm? It's like small mass. Because one disk is very small, right? Infinitesimally thin. So it's a small mass. Let's call it dm. So guess what? The total rod mass must be sum up all the small masses. So how to sum? Sum up from length equals to 0 to length equals to L. Okay, 0 to L. All right? So then you put in the mass of per disk. Then because your area is a constant, so you can take out. Okay? So this integral represents the total mass of the rod with varying density. Any questions? I hope with the examples that I've gone through, you somewhat get the idea of when is it that you need to perform an integration. Okay? Once again, when you have something that is changing, let's say density is changing along the rod, you want to find the mass, right? You got to integrate. You cannot just say, oh, it's density times volume. Density times volume is correct only for if the density is a constant. Okay? Density changes, you cannot just multiply, you have to integrate. Okay, so what is the rate of change of mass with respect to position? From here you can see what? So rate of change of mass with respect to position is exactly dm dx. So dm dx is just a dx, a rho of x. Okay? You just divide by dx throughout. So it's a times rho of x. So that's the rate of change of mass with respect to x. Is that all right? Okay? Any questions? Okay. Final question for today. Question 9. So actually question 9 not difficult. So you're just trying to prove why is it that your spring potential energy is given by half kx squared? Right? So you can see that I've drawn a spring here. Right? And consider that this sliding is frictionless. So what happens is that because your force in compression of the spring can be extension or compression, doesn't matter. Right? So this guy must be F equals to Kx, assuming that this is a linear spring. Okay? Linear spring it has means that it has constant spring constant K. Not all springs are linear springs. Okay? Gas springs are not linear springs. That means if you compress a column of air, right, it's not F equals to Kx. Okay? But if this is a Hooke's law spring, right, then this is a K. So when you compress along X, now the force that you are required to compress the spring must be Kx. So what you do, right, is that we are trying to get the work done. But we know that work done is just what? Force times distance moved. But yet, our force here is changing what? So the force here is changing along X what? So therefore, we cannot multiply. We have to integrate for the same reason that I mentioned earlier. So we just sub in the big F equals to Kx. Then you integrate this, you get Kx squared over 2, easy peasy. Then you sub in the limits, you get half Kx squared. So this is the reason why work done on compressing or extending a spring is half Kx squared. So what is the elastic potential energy stored in the spring? Then it's just by conservation of energy, because whatever work done you do in compressing the spring must go somewhere, right? So it must go into the potential energy of the spring. So you just use conservation of energy. The potential energy is the same, Kx squared over 2. Is that all right? So this will be the last question for today. All good, Good luck for your test later on. Okay? Yeah, that's all for today. Thank you. So I'll see you next Thursday. Right? Online in the Zoom lesson. If you cannot attend, it's okay. You can watch the recording. Okay? I'll also upload the writings as usual. Preferably, you also try out the past year midterms paper uploaded in Excite. Before I upload the full solutions, I will upload the full solutions, like step-by-step solution. Full solutions will be uploaded on Monday, coming Monday. Okay, but please don't wait until the solutions are uploaded and then you just go through the solutions. As I mentioned, you go through and you do from scratch. It's totally different story altogether. So please try first, then you compare your answers with the solution. Then you have a very good idea how much you can score. Okay? Yeah, so if you have any problems with the past year midterms, we can also go through on Thursday. Okay? So see you guys on Thursday then.